Section 7.3, anti-differentiation by parts, or also known as integration by parts, should be open to 7.3 in your packet. And on Friday, we wrote down this formula. The integral of u dv was equal to uv minus the integral of v du. And then I said where u and v are functions of x, or functions of some other variable. And I kind of just threw this formula up there, but today I want to show you where it came from and some examples of how to implement this technique known as integration by parts. So where does this formula come from? Here's how it works. Take two functions, u times v. Both of those are functions of x. And then you're going to take the derivative with respect to x of their product. So picture almost like we're doing a related rates problem. And u and v are functions of x, and we would take d dx of u times v. We have to use the product rule. So that'll be the first times the derivative of the second, which would be dv dx, and then plus the second v times the derivative of the first, which is du dx. And this equation is true based on the product rule and implicit differentiation. The next step, we're going to isolate this term u times dv dx on the left-hand side. So I'm going to imagine that I'm actually subtracting the v times du dx from both sides, and then I'm just going to rearrange it so that this is on the left. So algebraically, convince yourself that this is true, but it ends up looking like this. U dv dx will equal, and then we have d dx of u times v, put it in parentheses if we want to make that more clear, minus, and then v times du dx. Now, what's the whole purpose of this? We're deriving this formula, and then in a few moments, you're going to see how this formula can be used in some examples of integrals. But here's the derivation of the formula. We've got to go one more step now. We're almost there. At this point, we want to integrate both sides with respect to x. Okay, so I'm just abbreviating here. But what we're going to do is we're going to do the antiderivatives now, or take integrals of both sides with respect to x. So picture this. I'll use a different color briefly. Let me try red. Okay, so then I'm going to integrate now. And we learned you can integrate term by term. And when you integrate, you need a differential or a dummy variable that you're integrating with respect to. So we're integrating with respect to x. So I need a little dx wherever I put an integral symbol. And then, as you can see, this result, when you take the integral of this, well, here, the dx's kind of cancel out, so to speak. And we have now the integral of u dv equals, and then same thing here, the integration, or I'm sorry, it's not the exact same thing. Here, the integration and the derivative, remember those are like inverse operations. So taking the integral of the derivative, by the fundamental theorem of calculus part 2, we know that those are inverse operations which nullify each other. So we're just left with the function on the integrand, which is uv. And then over here, I'm going to do the same kind of thing where the dx's, I'm going to say that those cancel out, and now we have minus integral of v du. And that's the integration by parts formula, and that's how you derive it. Now, I know we were a little informal with the canceling, but this is an acceptable derivation for a first calculus course. Also, another saying to help remember this, because you do have to memorize this formula, uv minus the integral of v du. Some people say integration by parts is voodoo. As one of my teachers said, integration by parts is voodoo because, well, v du, it spells voodoo, so he thought that was easy to remember. uv minus voodoo, because it can get kind of tricky when you mix these up with u's and v's. Okay, so how do we use this method? Well, you need a couple of tips, some important tips. The first thing is, in general, you're going to be choosing a u, let me make this wider, about a couple bullet points. You're going to choose a function to be u, and another function to be v. Okay, and it's actually going to be really dv, but I'll just say u and v for now, really dv. And we'll see that method in a second. But your choice of which function is which depends on a couple of things. So that's the first bullet point. Secondly, there's some rules for how you should choose which function to be which. So in general, u should be easy to differentiate. Also, if possible, it should differentiate to 0 eventually. So if it's a polynomial, you take enough derivatives, eventually that would become 0. And then also in general, your choice of dv should be easy to find the antiderivative. Okay, and this will become more clear when we do examples in a moment. But your choice of u should be easy to differentiate, and your choice of dv, or the functions with v's in them, should be easy to find the antiderivative. And with that, let's go to some examples. Here's example 1. And one of the first things you want to notice is, well, why can't we use any other techniques on this problem? Why would we want to use integration by parts? And part of the reason is because none of those other techniques are going to work. If you think about it, if you let u equal cosine x, or if you let u equal x, as far as u substitution is concerned, or the substitution method, you're not going to end up getting the other term to cancel out, and you're still going to be stuck with an integral that you can't do. So we're going to attempt the integration by parts method, which in general, and maybe I should write this down, in general, the method is good for products of functions. Okay, and as you see more of these, you'll keep an eye out for like when I should use each method. But the integration by parts method is useful when you have like two separate functions and they're multiplied together. Now, it's true sometimes you can do that for u substitution as well, but integration by parts will be what we go for when u substitution does not work. All right, so let's attempt this example. We're going to let u equal x. So I'm going to make a little legend up here, kind of a 4-quadrant type thing. It has nothing to do with the coordinate plane. It's just where I'm going to catalog my substitutions. And I choose and make a choice for u. You'll see where I put them in a second. I'm going to let u equal x. X is an easy function, and eventually it differentiates to 0. Cosine x doesn't do that because it keeps toggling back and forth between sine x, cosine x, and negatives, and so forth. So I let my u equal dx. Then I need a choice for dv. So I'm going to let dv be the other part, call this the differential, and that's always going to contain the dx as well. So I'm going to let dv equal cos x dx. So what's that doing? Well, the goal of this is to rewrite the integral. We want to be able to rewrite it using our formula for integration by parts, which was the integral of u dv. So basically, the whole point of this method is that we are rewriting our initial integral we're considering it as an integral of u times a dv, and then we can rewrite that using the integration by parts formula, which is uv minus the integral voodoo of v du. So it's simply another way of substituting and rewriting things to end up with an easier integral, and the hope is that this integral over here will be easier to calculate. All right, so let's see what happens. Now, before we start plugging these substitutions in, we're also going to need to know the differential of u. So we're going to need du, which is going to be 1 dx. And you can see that because du dx would just be 1, and then you bring the dx to the other side. So we need that. And then we also need the integral of this, or the antiderivative, the indefinite integral, which would be v, and that's equal to sine x. Okay, so this little table, I like the way it's set up because when you're going down from here to here, you're differentiating, and when you're going up from here back to here, you're taking the antiderivative, or finding the antiderivative. And now we're ready to use this formula to calculate this integral. So what do we write? Well, the integral of x cos x dx can be rewritten as the integral of uv. Well, here's our uv, u times v, which is x sine x, and there's no integral there. They're just multiplied, so that's great. It's part of our answer, minus the integral of v du, which is sine of x, and then du is just 1 dx. And that's nice because we know how to find the antiderivative of sine x. So we're almost done. We just need to do that simpler integral. And we get x sine x. The antiderivative of sine x is negative cos x, but the negatives will cancel out. So we'll have plus cosine x. Don't forget, this is an indefinite integral, so our final answer should have plus c. And that's one example of how to use integration by parts. Let me show you one more example of integration by parts for today. This is example 2. And sometimes, kind of like when we did L'Hopital's rule, sometimes you needed 2 rounds of it to get the correct integral. When we do integration by parts, sometimes you also need to apply it more than once. So this is an example where we're going to need 2 rounds of integration by parts. But let's first make some observations. Why think integration by parts is a good method here? Well, if we look at the functions, first of all, it's a product of functions. And second of all, if we try to do u substitution, it doesn't seem to work well, because maybe I can let u be like x squared, and the derivative is x, but then my du is going to be stuck in this exponential function, and that's not allowed. You might let the u be e to the x, but there's no other e to the x, so it doesn't seem to work well for u substitution, and it's a product, so we're going to try anti-differentiation by parts. Again, we begin by choosing a u and a dv. And like with u substitution, you might start out with a certain choice, and it may not work, and you have to revise your work. And that's okay. But in general, I'm going to let my u be the function that's easy to differentiate and has a chance of differentiating to 0. So x squared, eventually when you differentiate that, it will eventually be 0. E to the x will never be 0. The derivative is just e to the x, and so forth. So I'm going to let that be my dv. E to the x, dx. Put the differential there as well. Then we take our derivative and antiderivative. So du would be 2x dx. And again, I'm getting that by saying du dx is 2x, and then I just bring the dx to the other side. But you can do that in one step. And then here, my integral or antiderivative of e to the x is simply e to the x. And then that's all. It's just itself. So we're ready to rewrite this integral with our integration by parts formula. So we need to do u times v, which is x squared e to the x, minus the integral of voodoo. Remember, integration by parts is voodoo. So v du. I need to multiply those, so I have 2x e to the x dx. And you might notice what happened. Yes, the degree got lower by 1, but this integral I'm still unable to calculate using another method. U substitution won't work. It's not a basic integral formula, so that's why we need to do integration by parts a second time. Set up your table with u and dv. My u will again be the 2x. That's easy to differentiate. And you could pull the 2 out here and then let x be the u, but I just wrote it, so that's fine. It'll work both ways. And our du is 2 dx. I'm going to let dv be e to the x again. And v is e to the x. And the reason I highly suggest writing out this table every time, because you're going to need all these components, u, v, du, and dv, to plug into the formula. So you're going to need it. You might as well finish that table off every time you do a round of integration by parts. All right, let's be careful here. We have x squared e to the x. We have a minus sign, and then this whole integral is getting rewritten. So I'm going to use a bracket so I don't forget to distribute a minus sign later. And then we have uv in this new integral, that's 2x e to the x, minus the integral of voodoo in this new arrangement. So voodoo here, or v du, is 2 e to the x dx. Almost done. Final step, x squared e to the x. And here we have minus 2x e to the x. And then this is going to be minus minus, which will become plus. And the integral of e to the x is just itself, so it's 2 e to the x plus c. Sometimes, if you notice, the AP test will present answers in a factored form. So you could factor out an e to the x in this case, and then you'll be left with e to the x times x squared minus 2x plus 2. And that's how to do integration by parts.